Today, my name is Indrajit and I am from Zensar Technologies. We we do a lot of research in AI, machine learning, deep learning, and reinforcement learning. One of such research that I am here to present, unfortunately, my researcher, she isn't available, both of them, and the other two researchers were Sudipta Mukhopadhyay and Zonunfeli Ralte. Now, I will walk you through the introduction, literature review, or drawback of traditional AI research in terms of this particular field, aims and objectives, data set, because this data set is very limited. And we were able to gather some data, and we thought, why not apply multi-arm bandits and specifically contextual multi-arm bandits. This is a novel study. It has not been done so far. We'll discuss about the results and as well as the future possibilities. So brain activity arises from electrical and chemical communications. We all know that. Few of the techniques that we use are EEG, and also we use F2, fMRI. These are some of the imaging techniques that we use. Now, if there are any abnormal firing of neurons that are captured in this? Now, understand that this domain of EEG is mostly a time series data. Now, there is a spectrograph that is available. When we convert that into an image, we get a spectrograph. Now, what happens in traditional, in terms of Gottman's time domain or RBFs or any kind of ELMs, that these are non-contextual aware. Even deep learnings or neural networks, they need a huge amount of data. Now, one of the challenge that we had is that we had limited data set because we did not collaborate with any of the, I would say, radiology clinic or anything as such. So we had limited data set, and that is the reason we wanted to test how contextual multi-arm bandits, how it helps in exploring and exploitation of the data sets. Now, I will move on to the next slide. So as you all know that reinforcement learning is mostly on a trial and error basis, and it's just like self-learning. You give a reward if the answers are correct in a very naive way. If the answers are correct, the AI engine or the deep neural network, which is here, it gets a reward, and based on the reward, it either exploits or explores. So what does that mean? Exploits, that means it repeats. Sometimes it tries to find the easiest solution, and once it starts exploring, it takes a longer time. Now, this RL is very limited in terms of biomedical domain because first, it's very costly to train, and secondly, it takes a lot of time to stabilize the neural network, and you will see how we have done it. In literature, this is one of the first studies that has been done, and that's what we thought that we will present this in AppsCon. Now, what we have also done is we have modified something called a EXP4 algorithm, which is a multi-arm contextual bandit algorithm. We have removed its traditional layers and got something new called transformers. The transformers are what ChatGPT, OpenAI, these people, they use the transformer layer for your large language model. And every expert will guide the decision making. So that's EXPD. We call our algorithm as EXPD. Now, I already spoke about this. And now there are a couple of, the objective is, as I said, that we have EEG signals. The signals has images, spectrograph, and the time domain. We take both of them together, and then we classify. Now, how we know that these are the right classification? We go ahead and there are some expert who has, I would say, voted them that yes, this is disease A, this is disease B, And I'll come to that. What are those diseases? Now, the one thing is real-time decision making. It generalizes pretty well than traditional, where a lot of feature engineering is there, or neural network, which prone to, I would say, overfitting. And definitely the integration is much more easier due to the inference hardware that is present at this time. So here is the data. As I told you that there are spectrograph and there are different diseases like, seizure, rather in terms of, if you don't want to call it a disease, it's more of a brain signals like, generalized periodic discharges, lateralized periodic discharges or LPDs, LRDAs or GRDAs, and seizures and others. Now, these are in rows. So you see all these are in rows, and on the column you have the votes. Now, what the contextual multi-arm bandits or EXPD, what it is learning are the features from two domains. The first domain is the image domain, the other is the time series domain, and it takes into an embedding layer. So we also have removed the traditional EXP4 layer and have put an embedding layer. So that means the two embeddings comes together and they sit together in a domain or in an embedding layer rather. So these two domains, when you consider them together, it's easier, or it helps to predict the disease better. And why does that happen is because some domain has its limitation, which are helped by an image. So if image is not able to let's take a step back. Let's say if an expert from the transformer layer is not able to go ahead and understand one domain, then it takes advantage of the time domain by comparing and seeing what is the cosine distance between both of the embeddings. And then the neural network processes it, or the transformer layers processes it. Now, first, one of the major thing that we need to do was create a Markov decision representation. So as you see that S or is the set of signals embedding from the transformer. So that's S. A is the classification of different diseases that I spoke about, or here it can be actions as well, in the sense predicting seizure, predicting LPD, predicting GPD. So it can be actions as well. Now we have to also create a transition probability, and which is describe the likelihood of moving from one I would say from one state to the other state, from a normal state to the seizure state. Now that's one. The very important thing is the reward function. Now this reward function is a cumulative reward. On the right hand side, you see that if the classes are correct, it gets 1. If the classes are incorrect, then it gets 0. And that's how classification also works. But that's actually rewarded. What is the goal of this algorithm? The goal of the algorithm is to maximize the cumulative reward and minimize a regret. So in the couple of slides, you will see that the regrets has been minimized. Now, yes, definitely there is a policy and as well as a T as a time horizon. Now, let's understand a couple of things is EXP or the recommendation via EXP4. So what this recommendation usually do? Now, what happens is there are, as I was talking about, that there are multiple experts, right? Every transformer head is an expert. So the experts, when it recommends that this is the disease or this is the abnormal signal, the model or the gateway, there is a gateway layer. The gateway layer will go ahead and moderate, and it will go ahead and create a collective information from all the experts. Now, it's just like an ensembling. So that's why it works better. So just think in that way, that it's not just one doctor or it's not just one radiology. There are multiple radiology telling, yes, this is the abnormal signal. And how are we knowing the ground truth? We do have the the rows which the columns which says yes, this is the vote that has been given by multiple experts. So that's how the reward function works. Now a little bit on the attention mechanism. There is a query, there is a key, and there is a value. And once the attention is computed by determining the relevancy of each input to the other. So A is equals to the softmax. So I'm not getting into the equation at this point in time. The output, the what is important is output of the attention. So each head will output a weighted sum of the value. Now here is another thing, that weighted sum of the values would be given as an output, and the age provides a unique perspective on the input data. Now let's go a little deeper. As I was talking about, that the output heads are combined or concatenated. So in the algorithm, we have concatenated, and M can be number of heads. Now there was a limitation on EXP4 that you cannot increase the experts. Now what we have mitigated that as well. You can add as much as transformer heads as possible, and that helps if the data grows. If the data grows, the transformer heads you can grow, and it helps most of the time. The backward propagation, that that the parameter is learned by weights of Q, K, B, and O. So that's also the idea, is to minimize the error as any neural network. Here is a comparison, what the improvement that we have got from EXP4 and EXPD, which is our algorithm. And so now it was trained on H100 GPU, a 40 GB GPU. The training went for almost like 5 days, or almost like 175,000 epochs or iteration it did. And as you see, the convergence, if I stretch it out, it's still little shaky. There are rooms for improvement here as well. But at the end, it did converge pretty well. Now, how do we know that our algorithm works better? We did a benchmarking. So we have done a benchmarking with neural networks. We have done a benchmarking with classical, which we are not showing here. But main thing that I wanted to show is, did it perform better in terms of deep greedy algorithm, or UCB, upper confidence bound, or Thompson sampling? Yes, it did pretty well, because as you see, the image is not that clear, but it's very much clear in our paper that the regret is very less. That means the model learned pretty well, and it's not trying to go ahead and exploit. When I say exploit, in the sense finding the easy way out, it's exploring and then getting into giving out the results. So this, these are a couple of the technical highlights which I have already covered. And what can be done in future? If we can go ahead and take a hybrid reinforcement learning approach, where I would say PPO, or proximal policy optimizations, and there are various others. If we can do, secondly, we can integrate this with our large language models these days, and finally, also non-evasive modalities, if we can go ahead and explore non-evasive modalities. So these are the things that we are going to do in future, and that's about it. If any questions, I'm happy to take.